There are two ways to measure how fast the universe is expanding. You would think it does not matter which one you choose. A ruler is a ruler. Distance is distance. Speed is speed. Measure the universe from one direction, measure it from another, and the two numbers should meet in the middle like a bridge built from opposite shores. They do not meet. One method looks at the nearby universe, the light of dying stars, calibrated with exquisite care, stacked into a ladder that reaches outward from our own galaxy. The other looks at the very beginning of time itself, the fossil light of the Big Bang, still drifting through space 13.8 billion years later. Two methods, two eras, two answers, and the gap between them will not close. For over a decade, the finest instruments ever built by human beings have tried to make these two numbers agree. They have failed. Every improvement in precision has not narrowed the gap, it has widened it. And now, a small number of cosmologists have begun to whisper something far stranger than a measurement error. What if the universe itself is not playing by the rules we gave it? And what if the force responsible, the one accelerating everything outward, forever, is not the fixed, eternal constant physicists have spent 30 years building their entire understanding of reality upon? Because if it isn't fixed, then nothing built on top of it is safe either. Not the age of the universe, not its fate, not the models 1,000 careers now depend on. This is a story about three cracks in the foundation of modern cosmology. Three separate, unconnected observations that should not exist, and yet all point toward the same unsettling possibility, that dark energy, the mysterious force accelerating the expansion of the universe, is not constant. It has a history. It may even have a future. But to understand why a handful of the world's most rigorous scientists are losing sleep over a discrepancy of a few percentage points, we first need to understand what it means to measure the universe at all, and why one of its earliest astronomers was dismissed for years before she was proven right. In 1929, an astronomer named Edwin Hubble noticed something that should not have been possible in a universe most scientists still believed was static and eternal. Distant galaxies were not simply floating in place, they were receding, and the farther away a galaxy was, the faster it appeared to be running from us. Space itself, it seemed, was stretching. This single observation gave birth to modern cosmology, and to a number that would come to define it, the Hubble constant. It measures, in essence, how fast every point in the universe is moving away from every other point, the expansion rate of existence itself. Picture a loaf of raisin bread rising in the oven. Every raisin moves away from every other raisin as the dough expands. Not because the raisins are traveling through the bread, but because the bread itself is growing between them. No raisin is the center. Every raisin sees every other raisin retreating. This is almost exactly what Hubble found happening to galaxies. For decades, refining that single number, how fast the dough rises, was considered a career-defining pursuit. And in the early 2000s, it seemed nearly settled. Then came Adam Rees. In 1998, Rees was part of a team studying a special class of dying stars called Type 1a supernovae, stellar explosions so consistent in their brightness that astronomers use them as standard candles, reliable enough to measure distance across billions of light years. What Rees found in that data would eventually earn him a share of the Nobel Prize. The expansion of the universe was not slowing down, as gravity should have demanded. It was speeding up. He was not alone in that discovery. On the opposite coast, a rival team led by physicist Saul Perlmutter had spent years racing toward the very same conclusion, cataloging the same class of dying stars, half convinced their own data contained some embarrassing error because the result made no sense. Gravity should be pulling every galaxy in the universe inward, slowly breaking its expansion. Instead, both teams, competitors, unaware for months how closely their numbers matched, found the opposite. The universe was pressing its foot down on the accelerator. Two rival teams, Two independent datasets. The same impossible answer. Something was pushing space apart. Scientists gave it a name for what they didn't understand: dark energy. But Rees did not stop there. Over the following 2 decades, he became obsessed, there is no gentler word for it, with pinning down exactly how fast that expansion was happening today in the nearby universe. Using the Hubble Space Telescope, then later the far more precise James Webb Space Telescope, his team built an extraordinarily careful cosmic distance ladder. Pulsating stars called Cepheid variables calibrated against supernovae, rung after rung, reaching outward from our galaxy into the depths of space. His answer, refined again and again: the universe is expanding at roughly 73 kilometers per second for every megaparsec of distance. And yet, there is a problem with this picture. An entirely different team, using an entirely different method, had already produced their own number, and it refused to agree. Imagine 2 surveyors measuring the exact same mountain. One stands at the base and walks the terrain step by step, measuring every incline with a level and a tape. The other photographs the mountain from a satellite and calculates its height using trigonometry and light. If their final numbers come out identical, you trust the mountain. If they consistently, stubbornly disagree, not by an error you can explain, but by an amount that only grows more precise with better equipment, you begin to wonder if you are somehow measuring 2 different mountains. This is exactly what is happening with the universe. The second team was not looking at nearby stars at all. In a control room in Europe, a collaboration of hundreds of physicists spent nearly a decade combing through the output of a single satellite, Planck, parsing microscopic temperature variations in light older than every star in the sky combined. Among them was Cambridge cosmologist George F. Stathier, who spent years defending the satellite's calibration, a debate that would eventually put the Planck team's methods under direct public scrutiny from rival groups defending the nearby universe number. For some on the team, it was the only project of their careers. Entire PhDs were spent studying a single patch of that ancient sky, hunting for fluctuations a few millionths of a degree apart, because those tiny ripples encode the entire physics of the infant universe. They were looking at the cosmic microwave background, the faint afterglow of the Big Bang itself, still washing over Earth from every direction, 380,000 years after the birth of the universe. From those fluctuations, using the well-tested equations of the standard cosmological model, physicists calculated their own value for the expansion rate, their number, roughly 67 kilometers per second per megaparsec, 67. On the surface, a difference so small it seems almost trivial. A rounding error, surely, something a better telescope would eventually resolve. Yet that is not what the data shows, as both measurements have grown more precise, as the error bars have shrunk from sloppy to exact. The disagreement has not vanished, it has hardened. Statisticians now describe the mismatch as a 5 sigma tension, a confidence level so high that in particle physics it would be enough to declare the discovery of an entirely new particle. This gap has a name now, the Hubble tension, and it means one of 2 things. Either there is a subtle, undiscovered flaw hiding somewhere in one of the most carefully checked measurements in the history of science, or the universe is genuinely behaving differently today than it did 13.8 billion years ago. To understand how strange this really is, consider what a 5 sigma discrepancy actually costs. A 1 sigma disagreement between 2 experiments happens constantly. Background noise, the ordinary friction of imperfect measurement. None of this is enough to worry anyone yet. A 3 sigma result might earn a raised eyebrow at a physics conference. Interesting, but inconclusive. The kind of anomaly that vanishes with a larger dataset 9 times out of 10. That number alone has never ended a career. A 5 sigma result is different. It is the same statistical threshold physicists demanded before they would announce, in 2012, that they had truly found the Higgs boson, a particle theorized for nearly 50 years before anyone dared confirm it existed. The Hubble tension has now crossed that same threshold, using two completely independent methods, calibrated by different teams, using different instruments, on different continents, separated by 13.8 billion years of cosmic history. But this still isn't the strangest part of the story. Because in the years since the Hubble tension became famous, cosmologists searching for its cause stumbled onto a second, unrelated crack in the same foundation. And this one concerns not the speed of the universe's expansion, but the shape of everything inside it. For most of her career, astronomer Wendy Friedman had staked her reputation on precision. In the 1990s, she led the Hubble Space Telescope Key project, an ambitious multi-year campaign to nail down the expansion rate of the universe once and for all using SIPED variable stars, the very same stellar mile markers Adam Rees would later use to sharpen his own number. Friedman's early results helped settle a decades-long feud in astronomy between rival camps who couldn't agree whether the universe was 10 billion or 20 billion years old. But by the 2020s, Friedman had become something rarer and more valuable than a confident expert, a skeptic of her own field's growing certainty. Using a different class of stars entirely, red giants near the tip of their brightness, rather than pulsating Cepheids, her team found an expansion rate that landed almost exactly between the two feuding camps, close enough to the early universe number to cast doubt on whether the tension was truly a crisis of physics or simply an unresolved crisis of calibration. The disagreement between Friedman and Rees, two rigorous scientists, two respected teams, two different starlit rulers, became, in its own way, a smaller mirror of the larger mystery. Even the experts studying the crack cannot fully agree on how deep it runs, and it was this unresolved argument that pushed a growing number of cosmologists to stop asking whether the measurements were wrong and start asking whether the model itself was incomplete. There is a version of this idea that some theorists find even stranger, and it comes from asking a different question entirely. What if dark energy was never one force at all, but two? Theoretical physicist Mark Kamionkowski was among the small group who proposed something called early dark energy, a second, short-lived burst of the same repulsive push, active for only a sliver of cosmic history, in the few 100,000 years just before the cosmic microwave background was emitted, and then gone, vanished. A brief, ancient flare of the same phenomenon now stretching the modern universe. No one has confirmed it exists. Think of it like finding two sets of footprints on a beach, one fresh, one buried under decades of sand, and realizing, with some unease, that they were made by the exact same shoe. If early dark energy is real, it would mean this repulsive force has appeared not once, but twice in the 13.8 billion year history of the universe. And nothing in physics currently explains why a force would switch on, vanish, and then reappear billions of years later. It remains speculative. But it is precisely the kind of speculation that stops sounding far-fetched once a second crack appears in the same foundation. And then a third. The Hubble tension concerns how fast the universe expands. But a second, quieter crack has emerged concerning something different: how clumpy the universe is. Matter in the cosmos is not spread evenly. Gravity has spent 13.8 billion years pulling matter into vast structures, galaxy clusters, cosmic filaments, immense voids of near emptiness stretching between them, like some galactic architecture built without a blueprint. Cosmologists measure the intensity of this clumping using a number called S8. Across observatories in Chile, Hawaii, and the Canary Islands, separate teams spent years chasing the same faint signal, the almost imperceptible way that distant galaxies' light bends and smears as it passes through unseen matter on its way to Earth. It is a signal so subtle that entire survey teams built careers around distinguishing it from noise, arguing for years over telescope calibration, atmospheric distortion, and the shape of a single pixel of light. Astrophysicist Catherine Hamans led one of the largest of these surveys, coordinating data from telescopes across 3 continents. And once they finally trusted their numbers enough to compare them against the early universe prediction, they disagreed. The early universe prediction, extrapolated forward from the cosmic microwave background using the Standard Model, forecasts one particular amount of cosmic clumpiness by today. But when astronomers directly observe the actual distribution of matter in the present-day universe, using that technique called weak gravitational lensing, they consistently find the universe to be slightly, stubbornly less clumpy than predicted, not by a small margin easily dismissed as noise, by an amount precise enough across enough independent surveys that it has earned its own name, the S8 tension. But this still isn't a coincidence anyone is comfortable with. 2 entirely different properties of the universe, how fast it stretches and how tightly its matter clusters, are both drifting away from what the Standard Model predicts. 2 cracks in 2 different walls of the same house. And when 2 separate cracks appear in a structure once thought solid, an engineer stops asking about the cracks individually. They start asking whether the foundation itself is shifting. 2 cracks now in the one structure every modern model of the universe's fate was built to stand inside. Picture yourself standing at the edge of the observable universe. Not literally, for no ship could ever carry you there, but in the mind's eye, at the farthest boundary from which light has had time to reach us since the beginning. Ahead of you, darkness older than any star, still expanding, still carrying the imprint of conditions that existed a fraction of a second after time began. Behind you, 13.8 billion years of galaxies forming, dying, colliding, in a universe of your own recent moment. 2 versions of the same cosmos, separated not by space, but by time. And the disturbing possibility now facing physicists is that these 2 versions of the universe are not perfectly consistent with one another. That something in the vast interval between them has changed the rules along the way. For over 2 decades, physicists built the reigning model of the cosmos, called lambda CDM, on a comforting assumption that dark energy, the force accelerating cosmic expansion, is constant, a fixed property of empty space itself, unchanging since the moment it first began to dominate the universe roughly 5 billion years ago. In the equations, it is represented by a single, unmoving number, lambda. But this still isn't what the newest data shows. In the high desert of Arizona, a robotic instrument the size of a small building spends its nights swiveling 5,000 tiny optical fibers, each one locking onto a single distant galaxy, each night collecting the light of thousands of them simultaneously. The scientists who built the Dark Energy Spectroscopic Instrument, DESI, had spent nearly a decade designing it for one purpose: to build the largest 3-dimensional map of the universe ever constructed, in the hope of finally cornering dark energy's true behavior. DESI director, physicist Michael Levy, had spent nearly 15 years working toward this single dataset, and when the anomalous fit first appeared on the team's screens in 2024, it was treated internally as a result requiring far more scrutiny before anyone was willing to call it real. They released their first results, nearly 6 million galaxies and quasars, charted across billions of light years, each one a fossil record of how matter clustered at a particular moment in cosmic history. And everything changes once again. When the DESI team compared their measurements to the predictions of a truly constant dark energy, the fit was imperfect, not catastrophically, not with total certainty, but with a persistent, nagging preference in the data for a different story. That dark energy may not be a fixed number at all. That its strength may have been slightly greater in the ancient past, and is slowly, almost imperceptibly weakening today. That was only the first year of data. A year later, in 2025, the DESI team released an expanded dataset. More galaxies, tighter error bars, a longer baseline through cosmic time. The preference for evolving dark energy did not disappear, it sharpened. If confirmed, this would not be a minor correction. It would mean the very thing physicists named lambda, the symbol for constancy itself, is not constant. It would mean the force reshaping the destiny of the universe has a history, a trajectory, perhaps even a future arc scientists have not yet mapped. For years, physicists have treated dark energy the way you might treat the pressure inside a sealed, inflated balloon. Assumed to be even, assumed to be unchanging, quietly pushing outward with the same steady force no matter when you check it. The new DESI data suggests something closer to a balloon slowly leaking, or perhaps one that was pumped harder in its early moments and has eased since. A force with a past, rather than a fact frozen at the beginning of time. Decades before DESI existed, physicist Eric Linder had already built the mathematics for a universe where dark energy shifts over time. A set of equations most of his colleagues treated as an unnecessary complication to a model that, at the time, worked perfectly well without it. For years, his framework sat mostly unused, a tool built for a problem nobody yet believed existed. When DESI's first results arrived in 2024, cosmologists reached for exactly the equations Linder had written years before anyone needed them. If dark energy evolves, then every calculation built on the assumption that it does not. The age of the universe, the ultimate fate of every galaxy, whether the cosmos ends in relentless expansion or eventual collapse, must be revisited. And it was this possibility, more than any single anomaly, that convinced a growing number of cosmologists that the Hubble tension and the S8 tension might not be two separate mysteries at all, but two symptoms of the very same underlying cause, a universe whose expansion has not followed one simple, unchanging rule across 13.8 billion years, but something stranger, still unnamed, still unmapped. A universe capable of quietly changing its own laws once is a universe capable of doing it again, and there would be no warning before the data was already years out of date. High in the Chilean Andes, an observatory named for Vera Rubin, the astronomer whose careful measurements of galaxy rotation first forced physicists to accept that most of the universe's matter is invisible, has just begun its decade-long survey of the entire visible sky. It was designed, in part, for exactly this moment. An instrument sensitive enough to sharpen both tensions into either confirmed discoveries or resolved errors, once and for all. Rubin spent much of her career being quietly dismissed by colleagues who assumed her data had to be wrong, because what it implied was too strange. It took nearly 2 decades before the physics community accepted that dark matter was real. The observatory built in her name may now settle a question just as strange. None of it is settled yet. So which is it? A subtle calibration error hiding somewhere in our telescopes, waiting to be found and quietly resolved, the way countless anomalies in the history of science eventually were. Or a genuine crack in the deepest model of reality ever constructed by human minds? The honest answer, in the middle of 2026, is that no one yet knows for certain. More data is coming. The Vera Rubin Observatory will spend the next decade photographing the entire visible sky in extraordinary detail. DESI itself will continue mapping galaxies for years to come, refining its still preliminary hint that dark energy is not constant into either a landmark discovery or a statistical fluctuation that quietly fades, the way so many 5 sigma anomalies have faded before. But for now, the cracks remain, unexplained, unresolved, and strangely, quietly thrilling to the very scientists whose life's work depends on the standard model being correct. Because if it isn't, if the universe truly has been changing its expansion, reshaping its own fundamental forces across billions of years, then cosmology is not standing at the end of a long and settled story. It is standing, once again, at the beginning of one. there is something almost comforting in the idea of a universe governed by fixed, unchanging laws. A cosmos with rules, stable and knowable, the same yesterday as they will be tomorrow. It is the kind of universe that rewards patience, that promises if we simply measure carefully enough, for long enough, the numbers will eventually agree. But perhaps the universe was never obligated to be that simple. Perhaps the force pushing galaxies apart has its own quiet history, its own arc across billions of years, indifferent to whether it fits neatly into the equations we have written for it. We are, after all, creatures who have existed for a few 100,000 years, attempting to describe the behavior of something 13.8 billion years old and still unfolding. The two surveyors are still out there, still measuring the same mountain, still refusing, after 30 years, to agree. The bridge from opposite shores has not yet met in the middle. Perhaps it never will. And somewhere in that gap, between the ancient light still arriving from the beginning of time and the galaxies still receding from us tonight, the universe may be quietly rewriting its own rules. We are only now, for the first time, starting to notice. Thank you for watching. I'll see you in the next one.